let's get started. So, good morning, everyone. Thank you for being here. It's great to see all of you here today. My name is Phil. I'm a staff engineer working at American Express. Today, we're going to take a look at coroutines. If you want to know how to use coroutines, you need to go back in time to yesterday to see Amanda's talk or catch the recording afterwards. Today, we're going to be talking about how these things work under the hood. So I decided to do something a bit weird for once, is that I'm going to start with the last slide. I'm going to start with the recap, which is what you should be learning today. And we'll show it at the end. So hopefully that works. So the goal for today is to understand that the Kotlin compiler will convert your suspendable functions to state machine. And this is how we can actually have non-blocking code. The state of the state machine is kept in a continuation object that we will see. And those continuation will wrap each other to create some sort of an artificial call stack that we'll be using. We'll also talk about threading and dispatchers today. So the threading happened on dispatcher. You've probably used them before, dispatchers main, dispatchers IO, dispatchers default. This concept is a generalization of continuation interceptors, so again with the continuations. We're doing Android, so we have the main dispatcher that is backed by a handler. If you've been doing Android for a number of years, you might remember the handler. We'll also talk about the default and IO dispatchers, which are actually backed by the exact same thread pool that can have an infinite amount of thread in it. And we'll just touch upon limited parallelism. That is a little less known feature, but that is very powerful for your apps. So with that out of the way, let's start at the beginning. So when you ask anybody what a coroutine is, they'll often tell you that this is, oh, it's a lightweight thread. And it normally show you an example in the sense of, we'll launch 1 million coroutines, we'll delay, we'll print something, and the impressive part is that it just works. And it is impressive that it just works, because if you try to do the same thing with threads, normally it will just crash, normally with an out-of-memory exception. So why we say that they are lightweight threads? Because, well, threads are a bit more heavyweight. They bring their own set of overhead. So for example, a thread normally will use 1 to 2 megabytes of memory for its stack. This is what is causing those exceptions. Also, the more threads you have, the more context switching you need to do. And those threads are also handled by the OS directly. So they're an important construct. We need them to be able to do parallel work, but they are a bit more heavyweight in general. So let's start again at the beginning. So when you want to do some blocking code, let's say you're a good old application where you are showing some progress indicator, let's say a spinner, and you do some blocking code in there, and then you want to hide your progress afterwards. The thing that's going to happen if you've done Android for any number of time is that, well, the main thread will be blocked and your spinner will simply stop spinning. So what do we do if we want to work around this? Normally, we'll go to something like a thread, probably through a callback-based API. So when using callbacks, it's again fairly simple. You've probably done that in the past. You're going to have a different method. You're going to pass in a callback to it. And in this method, you will call your threads. And once the parallel work is done, you invoke your callback again. So it works. We've done this for years. The problem here is that, for example, the callback here will be called probably on the background thread. So if it was Android, actually, that wouldn't quite work. The real problem that we get with callbacks is that once we start chaining them, we enter the good old callback hell. We see that the code all leans toward the right. It becomes a lot more complicated to actually figure out what is happening. It's not quite clear where the code will be running, on what thread, and there's a lot of duplication that is happening here, on top of having more allocation, because each callback that you create will be a new class, right? So this is our good old callback hell. It's more difficult to read. Error propagation becomes a bit more complicated there because you need to handle it at every single level in your callback chain. And also it's very unclear what thread you will be running on. So the way that we work around this, actually the new way to do this is with the good old coroutines, right? It looks a lot like the sequential blocking code, so we don't have that leaning to the right that we saw earlier. It will perform concurrently, just like callbacks with thread, but at the same time, everything could technically run on the actual same thread. So why am I calling about blocking and about callbacks? Because one thing I want to drive home today is that actually coroutines are just callbacks. We just don't see it. So coroutines are powered by a concept called continuation passing style, and this is not something that was invented by JetBrains here. This is a concept coming from functional programming. I think it's been around since the 70s or the 80s. But the point of the continuation is to have a general form of a callback that you can use to resume a function after the fact. So it's really just continuations or callbacks all the way down with coroutines. Those callbacks, yes, are continuations, and the continuations even hold some sort of state on that. And we'll talk more about the state they are holding later. We have an example of the continuation interface. It comes from the Kotlin standard library. It just has a resume with method plus a coroutine context. And this resume with method allows us to resume our coroutine with a result. So that's the result from Kotlin that we know and love. So that's either a success or a failure, which would be in general an exception. So let's see continuations in action. So let's re-implement the delay suspendable method from the standard library, from Kotlin X coroutines. So we're going to have a thread delay. It's a worse implementation. Please never do that. It's just for illustration purposes. So we're going to start by using the suspend coroutine method. So this comes from the standard library. This method, as the name would imply, suspends a coroutine. And what that means is that once we get there, the entire coroutine is blocked. Nothing can happen. So at this point, you can yield control of the thread so that another coroutine can run on the same thread. What happens that is interesting is that we get a block there, we have lambda, and we can have a continuation parameter. So in there, we're going to start our thread, we're going to sleep for, let's say, a second, and the contract for this method afterwards is that we need to call our continuation that resume with method. And that means that we are done suspending, we can resume. Maybe on the same thread, maybe in a different place, but now we are ready to resume this coroutine. If we never call resume with from this block, our coroutine will be blocked forever. So this is essentially our callback here. We can make it a little bit better. So in Kotlin X.coroutine, there's a different function that is called suspend cancelable coroutine. It serves the same purpose, but this is the one that you should be using because it will support cancellation out of the box. So if you are wrapping, by the way, a callback-based API and you want to have it work with coroutines, this is the way to do it. Use suspend cancelable coroutine. Another improvement that we can make is that there are a few extension methods on top of continuation. For example, just resume with the result itself with the success value, or there's a resume with exception if you want to resume with failure. One last thing that we can improve upon the previous code is not create a new thread every single time that we want to delay for a second. So for this, we can use one of the good old Java threading construct that we've had forever, for example, the executor services. So there's a specific executor that we can use that is a scheduled thread pool, and what it allows us to do is simply to execute a block of code at some point in the future. So with this final implementation, we actually have a fairly sensible delay method. It uses a single thread, and it will resume at the right time. It allows us to use coroutines properly. So that being said, let's take a look at what the compiler does to suspendable functions. So the way you usually go about this is that you go to Android Studio, there's an option to show the Kotlin bytecode, and after that there's an option to convert that back to Java. So what I did for this presentation is I took the resulting Java and converted it back to Kotlin to make it more readable. And I remove a lot of the optimization so that it's still understandable on the slide. So let's take a look at what happens when we decompile this simple hello world method. Well, a few things happen actually. The first thing that you'll notice is that the suspend keyword just goes away. This is not part of the bytecode. This is not understood by the runtime. This is only at compile that we have this. The other thing that we have is a continuation that is added to the parameters list. So this is normally the continuation of the method that called us, or this is our own continuation so that we can resume after suspension. We also have a new return type. Our hello world was returning units, so it was returning nothing. Now it's returning, well, anything. It's a nullable any. And this is what is actually powering suspension. And we'll talk about this later. And after that, since we have a new return type, Now we need to return something, so we're going to be returning unit. The one thing you might notice here is that we're doing nothing with the continuation itself, right? And the reason for that is that the compiler sees that there's absolutely no reason to suspend at this point. So it makes the optimization of simply returning immediately. So if we want to get more interesting code generated here, we need to add suspension into the mix. So we, again, just going to add a very simple delay method. So we basically added 2 lines here. So what does the generated code look like? It's generating a whole lot, right? So we'll go line by line to see what's happening. So what happens when we have suspension in a method is that the compiler will try to slice and dice the method to create a state machine out of it. The way it works, every time you see a suspension, you create a new state. Those states will be labeled, so it's going to be from 0 to however many states you do have. And you're going to have a continuation to back it up. This continuation will keep the state of this method. Whenever we resume a method, the current state, or the next state actually, will be stored into the label so that we know where to start from. So if we look at the code, how that's going to work, again, we have our hello method. It receives a continuation. It will wrap the continuation that it receives with its own continuation. This is where we're going to store the label. This is where we're going to store where we are in our method. And we'll see in a few slides exactly how that works. But what I want to draw your attention to right now is this one statement on the label. So this is where we are deciding what piece of code we should be using based on the label that is in the continuation. So here we are starting at label 0. The first line here is what we had in our own method. This was transferred to the generated code. So we're going to do our print line. We're going to set our label to 1 so that the next time we resume our function, we are going to the next state. And the meat of the suspension is here. So there are a few things to unpack in those 3 lines. So first of all, you can see that we're calling delay. That's the method from the standard library. And you might remember that delay A does not return anything, and B does not take a second parameter. Normally, it's just the duration. So in this case, delay is a suspendable method, so it is treated the same way as the one we would write. It is transformed by the compiler to add this continuation as the last parameter, and now it needs to return something. So let's look at what it's returning. It can be returning coroutine suspended. Coroutine suspended is a special value saying that we encountered a suspension point in the method, so we should return from this method and yield control of the thread so that another coroutine can run on this specific thread. So the reason that we need to return any, nullable any, is that the real return type should be a union type of coroutine suspended and the actual return type of your method. In this case, it is unit, could have been a string, could have been a class, could have been anything. So since we need to return one of those 2 things, it needs to be any. If we ever get union types in Kotlin, this is what is going to be used. So after this, what is actually happening here in this method? So when we are calling delay will receive the continuation of our own method. It will delay for a second, and in our implementation of earlier, it's just sleeping a thread. And at some point, it will resume that thread. And by resuming the thread, we will know that we are at the second label inside of our suspendable function, inside of our state machine, and we're going to be able to execute the rest of our method. So we're at that point. We've resumed our method, and we're now in state number 1. This is a new invocation of this function because we returned earlier when we returned coroutine suspended, but we are able to restore the method here and resume at the part after the continuation. So what I just said here is that we return from the method, right? It's a new invocation of the method. So in theory, we do not have access to the local variables that were in the function before because it's a brand new call. So how are we able to carry state over the different states in the state machine? Well, again, it's coming through the continuation. So whenever we have variables that we need to store, they will be stored inside of the continuation as in the first state. And when we restore the state, we will get it back from the continuation itself. And the way that ends up working is that in the decompiled code, in our first state, we will assign our variables as usual, store them in the continuation, and once we get to the next state, we are just restoring it from the continuation itself. Let's take a look at what happens when we have just a lot more states and more variables. So there's no limit to how many states you can have. So if we have two suspensions, we're going to have 3 states, and that works. And if we need to carry over more data across states, it's going to work as you would expect within the continuation. So on the first line, we have this variable hello. We're going to store it in the continuation. We're going to restore it in the subsequent state. If we have a new variable for it, we store it again in the continuation, and we can reuse it in the final state. But there's a but here. You might have seen this in your time as an Android developer. So you are debugging your code, you want to take a look at what was happening in the suspendable method before, and you get hit with this error message saying something to the extent that we are beyond, the variable is not used, it was not saved, it was optimized out. So what is the deal with this error message? Well, I oversimplified this earlier when I said that we are storing every local variable in the continuation. The compiler actually tries to be smart about it to reduce the pressure on memory and also reduce the size of the bytecode. So in this case, we are storing this hello local variable inside of an aptly named $0, remember, in the continuation. We're reusing it after that in the second state, but from the code you can see that we have no use for this lowercase hello afterwards, and the compiler knows that. So to save on memory, what it's going to do is just going to reuse this same variable into continuation to use the new variable. So there are ways around this. So there's a flag that you can set on the compiler to force it to do something more like the previous example, where it's going to keep everything in memory. This helps with debugging quite a bit, but it's not recommended to enable it for production code, mainly because it bloats the memory and there are good chances for memory leaks. So after this, let's take a look at loops. So what I said before is that whenever we have a suspension, we get a state. So if we have a loop that needs to suspend 10 times, how many states do we get? Like 1, 2, 10? We cannot really have one state per suspension because this could go on infinitely, right? So the compiler tries to be smart about it, and for each construct, there is a bit of a different behavior. So for this loop in particular, what is going to happen is that we're going to have 2 distinct states in our machine, 2 distinct labels. The first one is going to be to assign our I variable for the loop, and the second one is going to be actually doing the looping. So the only thing we're going to need to store for this is going to be I. So the code for this is a bit more complicated and harder to follow, so I'll do my best here. So we are starting this loop at var I is equal to 0. In our decompiled code, we have our var I, and we have a shorter when statement. So there's nothing that says that everything needs to happen in the wait statement. Stuff can happen after, as long as it stays correct. So in our first state, the only thing that we are doing is assigning the variable. And we won't even suspend at this point, right? We're just going to get out of that when statement. We're going to start our loop. It's going to be converted to a do while. We're going to increment our I variable. We're going to store it in the continuation because we're going to need it afterwards when we resume that specific loop. And yes, we're going to change the label so that we can start from there afterwards. Then we're going to do our delay. It's probably always going to return in this case, but if you were using a test dispatcher, it might return immediately. So while we do have this while loop here, it's a good chance that we're just going to return straight away. But the next time we resume our continuation, we will be back to this when statement in the new state, and we'll take the new value from I from where we stored it. And then we can go on with the method, and all of that by storing a single variable in the continuation and having a single, well, only 2 states. The last suspendable method that I want to decompile today is one with a try-catch right in the middle. We know that we cannot split a try-catch. Something needs to happen here. It's actually simpler than you might think to be able to do this, albeit maybe less efficient than you would think. The only way to go about this is simply to duplicate the catch statement. So it will preserve the same behavior, but it will result in a bit more code that you're not seeing, but that is still in the bytecode. So there's nothing wrong with catching an exception inside of a coroutine like this, as long as you're not like catching, exception or throwable or cancellation exception. Again, the two states that we're going to get here, try catch in the first, try catch again in the second. So just a bit more code that you would expect. So enough with decompiling suspendable method. Let's talk about call stacks. So we mentioned earlier that whenever we are suspending, we are returning from methods, right? So we still need to maintain this call stack somehow so that it makes sense in the debugger, so that it can make sense to preserve the ordering of execution. So when we first decompiled hello, I said that we were receiving a continuation, which was either our own continuation or the continuation of the method that called us. And this is where the call stack management is happening. So if we received the continuation from our caller, we will wrap it with our own so that we can maintain our own state, our own labels, our own variables, and this is what we're going to be using as long as we are in our method. And at the end, once we are finished with our method, we will call the resume with method of the continuation of our caller directly. So let's take a look at an example where we have three methods. We have main, we have foo, we have bar. Main will call foo will call bar. The output is on the right, is basically printing stuff. So let's start at the beginning. We are in our main method. We need to have a main continuation that is created. It's going well. We are entering our foo method. In foo, we're going to do our print line, and then we're going to call bar. So foo, what it did here, it got called with the continuation from main. It wrapped it with its own continuation, and it's keeping its own state in there. So we're going to call bar. Bar will do the same thing. It will wrap the continuation of foo. Delay, in theory, will do the same thing. It will still wrap bar. It will wait for a second, and it will call back its continuation with resume with. But at this point, we return from delay. Now we're going to return from bar, so we can return from bar. We can get rid of that continuation because we're done. It's pretty much the same thing as finishing a method. You just pop the stack at this point. We will be returning from foo. We're going to be doing the same thing again. We're back to main, and we can start this all over again. So this concept of calling resume with on all of the methods in the chain allow us to preserve our concept of a call stack. So the continuation that are generated by the compiler all extend from base classes. So we have the continuation impl interface and the base continuation impl. So resume with that we've seen so far come from the base. We cannot call it directly from our own continuation. So what we get inside of the continuation that are generated for your method is a single invoke suspend method. And the whole goal of this method is just to call the suspendable method with itself, with its own continuation. So this is what we are passing in as the continuation parameter. So the base continuation itself is where the magic happens when we try to resume one of our coroutines. So we will always resume with a result, but the way we're going to try to do this is that we will try to get an outcome out of the continuation that we are just calling. So this is where the invoke suspend method comes into play. So we're going to try to get a result. There's a chance that it's just going to say that the coroutine is suspended, in which case we will return all the way down up until we can tell the root that we are ready to yield that thread and that another coroutine can run there. Or if we are at the end of the coroutine, that means that we got our results, so we can unwrap. We will return our success, and we will resume our caller. So, how am I doing in time? Not too bad. Okay, let's move on to threading. So the continuation interceptor, this is something that you've been using a lot without knowing it. This is a construct from the standard library that is meant to be able to wrap a continuation with something else. So you get in a continuation, you return a different type of continuation. The whole point of this is to enable threading. So, and this is the basis for dispatchers. So let's take a look at how we could move some code to a background thread. So the way you would go around doing this is that you would create a new interceptor, make it implement the continuation interceptor, and then you would have a single method there called intercept continuation that takes in a continuation and returns a brand new one. And the brand new one that we want to return in this case is simply a continuation where we override resume with to put it on a different thread. So what we saw earlier is that when we call resume with, we are going through the state machine and we are executing the code. If this whole resume with is happening on a different thread, this is how we enable multi-threading. So, by the way, if you're seeing the word interceptor and you're thinking, oh yes, I can add logging, I can do a bunch of cool things, you're thinking about maybe OKHTTP interceptor, yes and no. So this interceptor is part of a context. And in coroutines, a context can only hold one value of a type at a time. So if you are overriding the continuation interceptor and you're setting a dispatcher after that, which one you set last will actually win. So continuation interceptor, it's a great implementation detail, but it's not something that you should be using in your day-to-day work. So with that said, you can use this interceptor as any other context element. So you can do it with context, you pass in the interceptor, and you're going to see that you are running on a background thread. And since this is in a context already, once you're out of it, we will resume on the main thread again. So the interceptor is what is backing the dispatchers. So dispatchers is something that you should be a lot more familiar with, right? So with context, dispatcher default, you do some background work. So the way that dispatchers are implemented, they are a subclass of interceptors. They override the intercept continuation method to be able to simply dispatch code to a different thread. There are three main methods that need to be implemented here. Normally, it's dispatch, to dispatch the code itself. There's a method to know if we need to dispatch that code or keep it on the same thread. And there is limited parallelism, which is something that you can actually use today and is very useful. So let's take a look at re-implementing the continuation interceptor that we had before using a dispatcher. There's a lot less code here. The main difference is that now it's dispatch instead of intercepting, and instead of creating a continuation, we're just getting a runnable. So it's much closer to what you would see with a handler or with an executor service. And again, if you just want to run it on a different thread, just run that thing. If you never use a runnable, it's just a simple interface from the Java world that has a single method called run. If we try to run this code, much like what we had with the continuation interceptor, it will be put on a background thread. However, the way it's implemented right now, there's a bug. Because since it's part of a context, every time we need to see if we need to dispatch, we're going to get that instance, and that instance always puts something on a new thread. That's the way we implemented dispatch. So if we were to run this code today, we would get two different threads for this, while conceptually we'd expect everything to stay in the same one because we're still in the same context. So this is where we have this is dispatch needed method that comes into play. The whole point of this is to determine if we need to run the code in place or dispatch it to run it in a different thread. So I re-implemented the previous dispatcher. It's slightly more complicated, but we'll go line by line again. I cheated a little bit to make it easier on one slide. So we're going to be using a single thread executor, again, construct from the Java world. We're going to set a specific name to our thread. We'll just call it my thread. And when we want to decide if we need to dispatch, we're just going to take a look at the name of the thread. And with this, it's a simple fix. It's simple, but it works for our use case. We're going to be able to actually have it run on the right thread in both cases. So that's kind of the gist of it for dispatchers. You need to determine how to dispatch, where to dispatch, and if you should dispatch it. So with that said, let's take a look at the dispatchers that we have available to us right now. So we'll start with the main dispatcher. This is the one that you're probably the most familiar with. The main dispatcher It represents the main thread. It's meant to be single-threaded. There's a limited parallelism method that is used to change how many threads you're using. It's overridden for the main thread dispatcher to make sure that you don't try to do something funky. And the thing is also that it's not installed by default. So if you try to start a command line project and you use the main dispatcher, it's probably just going to crash because every main dispatcher implementation needs to be made specifically for the platform that you are targeting. So we are getting one in Android, but you would have a much different one if you're targeting, let's say, Swing or JavaFX. The one from Android comes from the Kotlin X Coroutines Android library. So what does the main dispatcher look like for Android? I said earlier, it's based on a handler. So the handler is something that we used way back when we wanted to schedule code to run on a thread. So there were options to just post a runnable to run like on the next frame, post to run in a certain amount of milliseconds. It worked out well, but turns out that this is also the basis for what is happening with coroutines. So we have the coroutine dispatcher. The main coroutine dispatcher extends from coroutine dispatcher. Then we have the handler dispatcher and the handler context. For all intents and purposes, you can consider that handler dispatcher and handler context are exactly the same thing. So let's take a look at the code for the handler context. So it is based on a handler, and it also has an invoke immediately Boolean. So if you've ever used dispatchers that made it immediate, the way that it works is that if you're already on the main thread, it doesn't try to do a dispatch. So making dispatch in this case would mean posting to a handler, so it makes it slightly more efficient. So we have this method here. We have this isDispatchNeeded method that we talked about earlier, where we are determining if we should run it in place or try to dispatch it through the handler. First thing we're going to do is take a look at if we are in the immediate dispatcher. So if we don't want to invoke immediately, so if we're not immediate, that means dispatch all the time. So dispatch is always needed. But if we're on the immediate dispatcher, the way we're going to determine if we are on the main thread is by looking at the looper itself. Once this is done, the only thing that's happening here is that we are posting to that handler. You can mostly ignore what's in the lambda afterwards. It's in the case where the handler is getting disposed of. But the point is, you get a block, you get a runnable, just post it to your handler, and you're off to the races. All right. So let's talk a little bit about the other dispatchers. So we have two main ones that I want to talk about. So the default and the I/O dispatcher. The default dispatcher is mostly for for CPU-bound code. It's limited to the amount of cores that you have on your device. And in general, there's also a limited parallelism method that is very interesting that I learned about recently that we're not using nearly enough. So what limited parallelism does for the default dispatcher is that it gives you a way to get a view on the thread pool that you have. So let's say that you have some long-running operation. You know that it's going to hammer your CPU, but there's a lot of it, and you don't want to starve your thread pool. You can create a limited dispatcher that's limited to, let's say, one or two of the threads that you have in your default dispatcher. So that way, any other task that needs to run will still have access to this dispatcher, but you can make the choice of having those tasks take just a little bit more time to be able to all run. So they will also always be using the same thread pool for this. We also have the dispatchers.io, which is fairly similar. It's just that it's meant for I/O-bound tasks. So the way it's different is that we're going to start at 64 threads for it. It can be more than this. So if for some reason you had more than 64 cores on your Android device, you'd be using more than this. I don't think we're there yet, but never say never. The big difference here is that the limited parallelism call is not bounded. So it's a bit counterintuitive, but this wouldn't be a view on your I/O dispatcher at this point. This is a brand new dispatcher that if you wanted to have 3,000 threads in your thread pool for this, actually you could. The reasoning behind this is that for I/O tasks, you are not bound to the CPU. Most of what happens with the I/O dispatcher normally is that you are waiting for something. So you are waiting for data on a socket. You are waiting for your database. You are waiting for a file. So we make the trade-off here of using a bit more memory, but we don't pay the context switching costs so much. So we can have a bit more in this case. So it's always a different one. The last thing I want to talk about is the interaction between the default and the I/O dispatcher. So it's a bit counterintuitive, but those are actually exactly the same thread pool. They're all backed by the same threads, but the Coroutines scheduler is a class that is responsible for determining what should run when. So actually, even though if we think we have, let's say, 4 threads in our default dispatchers and 3 in our I/O dispatchers, those are all exactly the same thread. The scheduler itself will determine if a specific thread is assigned to one or the other. So the limits that we set up, either through using the defaults or through limited parallelism, are just enforced as that, as limits. We're not guaranteed to run on specific threads, so your thread ID could change, but you are guaranteed that you will never go above a certain number of threads. And this is very powerful, and I think that the scheduler itself could be a talk all in itself. It implements work stealing algorithms, it's fantastic. But the gist of it is that if you are using the default dispatcher a lot and work is ramping down, and now you need to do a bunch of I/O, well, there's a very good chance that the thread that is going to run after that for I/O will just be one of the default dispatcher threads. So another interesting thing with this is that on a best effort basis, if you ever need to switch from default to I/O, let's say you are in the default dispatcher, you do a with context and do something on the I/O dispatcher, actually what is going to happen here is there's a good chance that you will just stay exactly on the same thread because it's all the same shared thread pool. So it can just be reused. So you're saving a context switch, which will make your code a bit more efficient in this case. And actually, yes, that's all we had for today. So we're back to the recap slide. So let's see what we covered. So what I wanted you to get out of this talk is that the Kotlin compiler will convert your suspendable functions to state machines. These state machines will have a state. That state will be contained inside of a continuation. After this, those continuation will wrap each other to generate a call stack. After this, for threading all happens on dispatcher, which is a generalization of continuation interceptors. For the main dispatcher, there's no magic here. It's just using a handler from Android. The default and the I/O dispatchers are sharing the same infinite thread pool. And limited parallelism is awesome. You should use it a lot more. This could improve the performance of your app. And that being said, thanks a lot for being here today. I'll be able to take questions afterwards.